Welcome, everyone. Today, we are going to explore the two-system pattern, a powerful architectural approach for modern cloud-native applications. This pattern focuses on uniting what we call the cluster nervous system with a robust enterprise gateway. Specifically, this is a reference architecture for integrating NATs running on Azure Kubernetes Service, or AKS, with Azure Event Hubs. On the left side of our diagram, represented by the green circle, we have NATs acting as the internal nervous system. Within an AKS cluster, NATs provides high-performance, low-latency messaging that connects your microservices with incredible speed and efficiency. It is designed to handle the complex, high-frequency communications required within a localized environment. On the right, represented by the blue circle, we have the Enterprise Gateway, powered by Azure Event Hubs. This component is designed for massive scale and serves as the primary entry and exit point for data across the broader enterprise. It excels at long-term event streaming and provides the durability and reach needed to interface with external systems and services. The orange bridge connecting these two circles represents the critical integration layer. By uniting the agile internal messaging of NATs with the massive throughput of Azure Event Hubs, organizations can achieve a seamless flow of data that is both incredibly fast locally and highly scalable globally. This architecture ensures that your nervous system stays responsive, while your enterprise gateway remains robust and connected. This best of both worlds architecture leverages two distinct messaging systems to handle specific traffic patterns within our ecosystem. On the left, the cluster nervous system manages east-west traffic using NATs. This provides the high-frequency, low-latency internal communication essential for microservices. On the right, the Enterprise Gateway handles north-south traffic through Azure Event Hubs. This provides a durable, massively scalable ingestion point for data intended for the broader enterprise. It serves as the formal, robust entry point to our cloud ecosystem, facilitating long-term retention, big data ingestion, and external service integration. By combining these two approaches, we achieve maximum internal agility alongside enterprise-grade durability and scale. This high-level architectural pattern demonstrates how to integrate internal microservices with external data consumers. At the heart of the architecture is an Azure Kubernetes Service cluster. Inside this cluster, multiple microservice pods use a NATs cluster as a high-performance messaging backbone for internal communication. To export this data, we utilize a bridge pod, which acts as a gateway connecting the internal NATs cluster to Azure Event Hubs. Once events reach Azure Event Hubs, they are distributed to various downstream services. These external consumers include Azure Stream Analytics for real-time telemetry processing, Azure Functions for serverless event handling, and Power BI for live data visualization, ensuring a seamless flow of information from the containerized environment to actionable business insights. Let's transition to seeing how this pattern operates in practice by examining three core use cases. We will explore how this architectural approach solves significant real-world challenges, specifically focusing on IoT ingestion, domain event exposure, and hybrid cloud replication. These examples demonstrate the versatility and effectiveness of the pattern across diverse technical landscapes. In this first use case, we examine the edge-to-cloud buffer designed for efficient IoT ingestion. A common problem in IoT architectures is that high-velocity, small messages from numerous devices can quickly overwhelm Azure Event Hubs or lead to excessive costs due to per-request pricing models. To solve this, we utilize NATs as a high-speed, in-cluster buffer within an Azure Kubernetes Service environment. As the diagram illustrates, IoT devices send their data into a NATs cluster. From there, a specialized bridge pod subscribes to these NAT streams. This pod aggregates thousands of these small individual messages into a single compressed batch, pushing an efficient payload to Azure Event Hubs. Once the data reaches Event Hubs, it is distributed to downstream services such as Azure Stream Analytics, Azure Functions, and Power BI. The key benefit of this approach is twofold. It dramatically reduces Event Hubs costs by minimizing request volume and effectively decouples internal traffic spikes from cloud ingestion limits, ensuring a more stable and cost-effective ingestion pipeline. In our second use case, we examine the cluster gateway pattern for managing domain events. Within a typical microservices architecture, services generate two distinct types of events: high-frequency internal implementation chatter, such as session updates, and high-value domain events, like the creation of a purchase order. The challenge lies in preventing noisy internal traffic from overwhelming enterprise systems while still exposing critical business data. Our solution involves implementing a smart bridge within the Azure Kubernetes service cluster. As illustrated in the diagram, microservice pods communicate through an internal NATS cluster. While the vast majority of traffic remains local to the cluster, specific high-value events are published to designated public subjects, such as public.orders. The bridge pod acts as a policy enforcement point, specifically configured to subscribe only to these public subjects. This bridge then selectively forwards these domain events to Azure Event Hubs. The key benefit of this architecture is that it keeps internal NATS traffic private and high-performing, while securely exposing a stable event contract to the wider enterprise. In our third use case, we examine hybrid cloud event replication. This scenario involves an on-premise AKS cluster, such as one on a factory floor, that requires sub-millisecond real-time messaging for its local operations. While local speed is critical, there is also a need to synchronize audit data to a central cloud for high-level analytics. To solve this, NATS is deployed locally to handle all real-time messaging requirements. Complementing this is a replication bridge pod, which asynchronously pushes data to Azure whenever connectivity is available. As illustrated in the diagram, the local NATS cluster ensures the factory stays operational regardless of internet status. This design provides a significant key benefit. Local operations remain resilient and performant because they are not dependent on a continuous cloud connection. Any accumulated data is simply synced to Azure Event Hubs once the connection is restored, allowing for seamless downstream analytics and visualization in Power BI. The blueprint for building the bridge pod focuses on a lightweight, containerized service rather than an out-of-the-box connector. This approach requires you to build and deploy the service manually to ensure maximum flexibility within your architecture. Utilizing NATS as the core messaging technology, we have developed a reference implementation in Go to serve as the foundation for your deployment. The core logic of a message bridge can be understood through a consistent 6-step pattern. This example illustrates how to bridge an internal NATS service to Azure Event Hubs using a reliable at-least-once delivery model. First, the bridge establishes a connection to the internal NATS service. In the pseudocode, we initialize the connection and create a JetStream context, which provides the necessary features for robust message handling. Second, we connect to Azure Event Hubs by creating a producer client. This client is configured using a connection string to ensure secure communication with the target cloud resource. The third step involves subscribing to a specific NATS subject, such as events.greater-than. This tells the bridge which streams of data it is responsible for capturing and forwarding. Once a message is received, step 4 is transformation. We convert the NATS message into an Event Hubs event data object. This includes mapping the message body and adding relevant metadata, like the original NATS subject, into the event properties for downstream use. In the fifth step, we send the data to Azure. To maximize performance and efficiency, events are typically added to a batch and sent collectively using the producer client. Finally, the bridge acknowledges the message to NATS. It is critical that this acknowledgement happens only after the message has been successfully sent to and confirmed by Event Hubs. This sequence ensures that if a failure occurs during the transfer, the message remains in NATS to be retried, guaranteeing that no data is lost in transit. In this deep dive into production-ready code, we focus on initial configuration and service connections. Starting with the global variable block, we see that configuration is decoupled from the application logic by using environment variables. This approach is a standard best practice for containerized applications, particularly in Kubernetes, as it ensures portability across various environments without requiring code changes. Within the main function, the implementation prioritizes resilience through a graceful shutdown mechanism. By using context with signal notification for interrupts and termination signals, the application is designed to catch signals from the orchestration layer. This allows the system to complete any active processing tasks before shutting down, preventing data loss. Lastly, the code establishes robust connections to NATS JetStream and Azure Event Hubs, utilizing the previously defined environment variables to securely and flexibly manage external service endpoints. The smart batching loop shown here is designed to optimize both latency and throughput while ensuring high reliability. To prevent messages from stalling during low traffic periods, we implement a flush on timeout strategy. A ticker triggers at a defined interval, ensuring that any messages currently in the buffer are sent, regardless of the batch size. This maintains a predictable maximum latency for every event processed. To maximize throughput during high traffic bursts, the loop utilizes efficient batching. The logic attempts to fill each batch to its maximum capacity before transmission. If the batching function returns an error indicating the batch is full, the system immediately dispatches the data. This approach minimizes network overhead by consistently sending the largest possible payloads. Data integrity is maintained through the guaranteed delivery logic found in the send and ACK helper function. By only acknowledging the source messages after the batch has been successfully received by Azure, we achieve at least once delivery semantics. This architecture ensures that no data is lost, even if a failure occurs during the transmission process.
This slide highlights the key design decisions made for this architecture. First, the use of queue-subscribe sync enables horizontal scaling by allowing multiple replicas of the bridge pod to run simultaneously. NATS automatically load balances messages across these pods, and if any single instance fails, messages are seamlessly redelivered to a healthy one. Second, we utilize manual ACK to explicitly control when a message is acknowledged. By waiting until after the Azure send is confirmed, we prevent data loss in the event of a mid-process crash, ensuring at least once delivery. Third, the ticker flush mechanism balances throughput with latency. While full batches are preferred for efficiency, we must ensure that single messages do not wait indefinitely. A 100 millisecond flush guarantee provides a consistent maximum latency, even for low-volume streams. Finally, we prioritize metadata preservation. By injecting the original NATS subject into the Event Hub message properties, we preserve vital context. This allows downstream consumers to identify the exact origin and topic of the data, maintaining end-to-end visibility.
The synergy between NATS on AKS and Azure Event Hubs creates a powerful messaging ecosystem that balances performance with durability. On one side, we have NATS on AKS, which provides ultra-low latency of less than 1 millisecond. Its lightweight protocol is perfect for high-speed internal communications. While retention is limited by the underlying hardware, the cost is fixed and predictable based on compute resources. Conversely, Azure Event Hubs offers moderate cloud-based latency and supports robust protocols like AMQT and Kafka. Its primary advantage is infinite data retention via the capture feature, governed by a usage-based cost model. When we combine these strengths, we get the best of both worlds, a real-time edge coupled with a durable cloud infrastructure. This allows for efficient internal communications alongside a reliable long-term archive. We also gain the ability to optimize costs through intelligent batching, utilizing NATS for high-frequency traffic before moving data into the usage-based Event Hub storage. This architectural pattern provides an elegant solution for hybrid messaging by combining the unique strengths of two powerful platforms. By treating NATS as the high-speed internal nervous system and Azure Event Hubs as the robust enterprise gateway, we create a decoupled, resilient, and cost-effective messaging framework. This strategic integration allows us to achieve low-latency performance for internal operations while maintaining the enterprise-grade reliability required for external-facing gateways.